Hi everyone. As Miguel introduced, my name is Carlos, and I'm spending my research time in my PhD researching on a novel methodology to create more enjoyable motion controls in virtual reality games. I am a PhD student at the University of York, and I am very lucky to be supervised by two really experienced professors. One is Professor Sebastian Ditterding at the University of York and Imperial College London, and the other one is Professor Marco Gillis at Goldsmiths University of London. And I'm basically before entering the PhD and being supervised with this amazing team, I was a very active independent game developer, and I got really into the virtual reality game scene back in 2016, where the Oculus Rift, the HTC Vive were released. You had this explosion of possibilities where gaming and a new form of media was appearing, and I was like, oh my god, I really want to research on this. So my motivation spanned from my previous work as well, where I was working with game controls a lot, it's something that we many times give for granted, but it's actually very important for both interaction and also for the programming side, because they are the first thing that players encounter in their interaction with a video game. And we know that they affect player experience. We know this as developers. We want the game to feel the best way possible. We want the controls to be smooth and consistent among games. But at the same time, in game psychology research, there is plenty of evidence that good game controls have a positive effect on the player experience. The problem with virtual reality, which is not that big of a problem in non-virtual reality settings, is that there's a wide variety of motion controllers and there is very little established practice. The Vive wand, which is the ones you see at the bottom left of this screen, they don't have joysticks. And the newer version of the headset still doesn't have joysticks. The PlayStation counterpart doesn't have joysticks, whereas the Oculus and all of the Oculus-like headsets, they do incorporate joysticks and a different button disposition. And there is as well the possibility of using hand tracking in virtual reality. So it's the input dimensions here are very different, too different, right, to standardize something. So how game developers reach solutions that will work among all of these different families of controllers? Well, there is a solution that I call direct input mapping. Here is a little snippet from a game called Job Simulator, which is really fun, in which you are basically the last human on Earth in a world overridden by computers, and computers are fascinated by how could you do such mundane tasks so often. So you need to do a job in the eyes of a computer. And here is very clever because the inputs, the way the inputs are mapped, it's independent of the controller. It's basically you just grab something, you launch something, and you use movement very directly, right? There is no processing behind your movement of any kind. Another solution is directional vectors. Again, here your controller can have these shaped ones, and basically you're using simple direction vectors to slash cubes. The cubes that have an arrow on the bottom or the top, you basically need to do vertical movements. The ones that have an arrow on the sides, you need to do horizontal movements. And it's an extremely widely successful game, a multi-million-dollar company already that created Beat Saber. If you haven't played it and you know you have any friends with VR headsets, you should try it. It's a great experience. You feel like you are both dancing and working out, and I don't know, it's a great experience. And then here is the most problematic field. When developers and designers want to incorporate nuanced gestures, because of the way the game development pipeline works and the lack of machine learning expertise, they do end up having hard-coded gestures with very long files, and it's very complicated to make any changes. So for instance, here is an example of a archery gesturing control scheme. And I've seen the source code for different implementations of this, and it's a real pain and real time consuming to make any modifications, up to the point where in many games, even though you have this bow and arrow to use, it just doesn't feel good and you end up not using it. And if people want to mod it, modding that, it's a huge nightmare. So this particular area could benefit from some design and technological interventions. So in not only that, but we still don't know what can make a VR game feel good, enjoyable, and natural. And we should have a methodology, we should have ways for designers to quickly experiment, prototype, and run user experience studies, which is currently not the case. Prototyping VR games is still quite a time-consuming activity, especially if you want to create more nuanced, novel movement interactions. And future VR systems will presumably incorporate more sensors. Actually, this is a fact. We know that the next generation of PlayStation VR systems are going to incorporate eye tracking by default and certain haptic sensors. And Facebook and Apple, we know they're working also on novel sensors to incorporate into their headsets whenever they are launched. They're playing with potentially smell. They're playing potentially with some sort of haptic feeling on your nostrils. It's like it could be really the dimensionality of inputs and outputs can increase. So this is my solution. I basically, in my PhD, I've been researching with different, I think, honestly, playing around with different solutions and seeing what worked and what didn't. Of course, following the, as much as possible, the evidence and user-centered design process. And I came up basically with this idea where we do have a process, prototyping process, that it's broken up into 3 steps. First, the ideation step, second, implementation, and third, the evaluation. So the ideation step, it's quite interesting because when we were about to start the running studies, the pandemic started. So I couldn't do these studies in person. So I was forced to look at a remote setting for ideation. So of course, I'm working with VR, so social virtual reality environments are an obvious choice. And it was a great, really, really fun to do this, to do these workshops there, great experience. And basically participants are tasked with ideating interesting and novel movements by bringing movements that they like from existing video games. It could be the jumping from Mario, or it could be, I don't know, you create a portal with your hands to enter another world from Doctor Strange. And then they are tasked with, all right, so let's follow a somatic activity where you use your bodies, you use your embodied cognitive capabilities by imitating each other's movements, and you create novel movements by either combining existing movements or picking something that you felt with your body was nice, and coming up with interesting ideas that feel nice at the moment of ideating without thinking about implementation. Then the second stage, implementation, we ran a few workshops. We are running more in this summer in case you are also interested, if you want to spread the word. And basically we have a toolkit where we are in Unity, and it's a visual scripted toolkit. And basically you can prototype by example and train machine learning systems using an interactive workflow. And you can play with our technology and see what feels nice quickly. And finally, the evaluation part, which is also part of the study I'm running this summer, basically is a very big question in creative machine learning applications, and how do developers and designers evaluate what feels good and what doesn't feel good. And of course, this evaluate what does feel good is a multidimensional construct. So there's more to unpack there, but I don't have the time to go through that. But the fascinating field, both from a design and psychology perspective. So we did this study on the remote settings, and we actually compared both video calls and social VR to find a suitable remote setting. And we did find a very strong effect in social virtual reality, because in video calls, we cannot see who is going to talk. We cannot see who is looking at us. So in social virtual reality, even though you have these avatars that are not really representing yourself, turn taking was smoother, joint attention was happening. For instance, here on one of the images, there is a group of participants talking about an interaction with a dog, where they were using a toy fish as the prop. and they were basically petting the toy fish as if it was a dog, and everyone was like, yeah, you can toy the dog this way, and then you're petting the dog this way, and you're giving the dog superpowers. And they were really engaged into the explanation. So this ideation aspect in social virtual reality, actually, it's a really interesting finding that we were not expecting when we first started, right? Because that wasn't the focus of the study. And the implementation part that I briefly introduced before is done with InteractML. InteractML, it's a interactive machine learning framework that is all visually scripted in Unity as a plugin. It was born out of a project that I worked on, funded by Google and the EPSRC in the UK at Goldsmiths University of London. And it's completely free, it's open source, it's MIT licensed. So if you want to play around with it, the website is interactml.com. You have also the GitHub link to check the source. It has a native VR interface. It has native support for Arduinos. You can extend the functionality. And if you're more interested, please get in touch through the Slack, because we are going to run workshops in June, July, and August, and you can learn for free, and you will be taught how to use these, and you can create something fun that might be potentially useful for your research. I don't know. So I think this is mostly my presentation. So I try to keep it as short as possible. It's around 11 minutes. So please, if you have any questions, feel free to ask, and thank you so much for listening.